Thank you. Steve Jurvetson really needs little or no introduction here in Northern California, but his background crosses over so many areas that I consider it the new wave, so to speak, in venture capitalists, although not so new. Steve is managing director, of course, of Draper Fisher Jurvetson. He was the founding VC investor in Hotmail, Interwoven, and Kana, lots of others too, and also leads the firm's investment in TradeX, CITRIS, Posit Science, and so on. He started in R&D, interestingly enough, at Hewlett-Packard in areas like communication chip design, where he saw his chips fabricated, also hands-on work in programming and material science. Steve has worked in product marketing at Apple, at Next Software, and as a consultant with Bain & Company, a well-known VC, where he developed executive marketing, sales, and business strategies for a wide range of companies that they work with in networking and semiconductor. At Stanford, he finished his BSEE in 2.5 years and graduated #1 in his class. He also holds an MBA and an MS in EE from Stanford. Steve was honored as the Valley's sharpest VC on the cover of Business 2.0 and chosen by the San Francisco Chronicle Examiner as one of their top people going forward. Lots of great awards and honors that he's received, and lots of, in fact, well-deserved recognition. He was also chosen as having his work, what he does, is having the greatest impact in the Bay Area in the 21st century, or a candidate for going forward, of course. He's been profiled in the New York Times Magazine, featured on the covers of Worth, Red Herring, and Fortune. Steve was chosen by Forbes as one of the tech's best venture investors, by the VC Journal as one of the 10 most influential VCs, and by Fortune as part of the Brain Trust at Top 10 Minds. Steve?
Thank you. Wow. Thank you. Wow, with an introduction like that, I'm certainly going to disappoint. So let me try to be a bit more humble and say, since I'm a domain expert on none of the subjects, but I'm fascinated in all of them, I'm going to just confabulate on the fly here and try to come up perhaps with some generalizations, perhaps something that even feels like philosophy more than anything else, around some of the approaches that I see common to a lot of the research for the future: how to build cognition in computers, how to build thinking machines, how to build complex systems that are robust and resilient. And as I've looked across a number of these, from the Santa Fe Institute projects to a bunch of startups, some interesting patterns emerge. I'll try to share just one coarse generalization with you, and hopefully it'll spark some thinking. Just one slide on us. Let's see if I can make this work. No, I can't. So this may be... Oh, yeah. We're a venture capital firm, just for context. So we don't do primary research. We're not really contributing to the economy in any direct way, but we get to invest in bright, brilliant entrepreneurs who really make a difference and try to change the world. We're an early-stage venture firm. We have offices around the world in an unusual structure of affiliates. We manage about $4 billion, but we try to invest in startups that are truly revolutionary. Posit Science was mentioned a couple of times. That's Mike Merzenich's company that's developed a software training program that seems to shave 10 years of cognitive decline, age-related cognitive decline, off of individuals who go through a one-week training exercise. Other companies I've personally been involved with of late include a quantum computing company that's demonstrated a 16-qubit solid-state quantum computer and hopes within a couple of years to have 1,000 qubits, which would be a very interesting resource for molecular modeling or modeling any quantum mechanical system of comparable complexity, and modeling it perfectly, solving Schrodinger equations, for example, in polynomial time. And a third, very different kind of company, but I think in some ways all interrelated, Synthetic Genomics, which is Craig Venter's company, which in a few months will hopefully announce the first completely synthetic life form that lives and propagates and built base pair by base pair from the ground up. So look for that in the next few months. And all these projects have something in common, which is they're trying to deal with very robust, complex systems, and they're trying to introduce some element of engineering into a process that's barely understood, where the systems theory isn't fully borne out, but where they're big unsolved problems. So this led to some interesting questions. What is it about building complex systems that are interesting? What are the two major paths that I see, if you were to really do a very coarse generalization, that I see researchers proceeding forward along? And if you look at the big unsolved problems in a variety of fields, be that computer science, the things that just aren't trivial problems, the things that are really interesting to researchers. In the field of nanotech or synthetic biology, it usually evolves about how can you build complex systems? How can you make something that's robust and resilient over time? And one specific example that I'll spend a little time dwelling on that might be relevant to this group would be, for example, how would you build something really audacious and really complex, like a general artificial intelligence that exceeds human intelligence? If you think about that sort of future tractor, that star in the sky of the future, how might we get from here to there? And there are two major paths that I see. Harkening back to the early days of the field, it could be the neural network bottom-up approach versus the sort of rules-based top-down approach. I think today there'd be much more sophisticated descriptions of this, but there are definitely iterative algorithms from which, from a sort of modeling or inspired model from the neuron, we build up to an intelligence that we don't design every element of. And then there are still some of those out there who I debate with quite a bit who think we're just actually going to be smarter than that and we're going to build the whole thing from scratch, from the top down, using traditional computer science techniques. So if we look at those two paths, if I describe them very coarsely as a design, purposeful design, intentional design, versus evolutionary search. And by this, I don't just mean evolutionary algorithms. This could be genetic algorithms. This could be high-throughput experimentation. This could be trial and error experimentation in the crudest form, but accumulating purposeful design over many iterations. If I take that approach, you can make some generalizations about them. And the point I want to make, the reason I think this might be interesting, I'm sure I've said nothing new so far to any of you, is that I see many researchers in this field mixing and matching between these two paths as if they were interchangeable. For example, as if you could evolve a brain and then re-engineer it, or cut and paste its subcomponents, or port it from the human cortical substrate to a computer, as Ray Kurzweil would describe. And while many of those processes may be possible, I think some may be more difficult than others, and we don't have theory or even a reason to believe some of these things may be possible. So specifically, I think they're very different. I'll get into that. And I guess one last thing, if I haven't revealed a bias, I think the bottom-up approach seems more likely, seems intuitively like the path to the future. And at least biological evolution gives us the only existence proof of a complex system being created that is more complex than its antecedents, right? And we see this around us. No human has designed an artifact purposefully all in one that is more complex than themselves. They've only created a process by which more complex systems can be built. So I could have quoted from many books, but since we just heard from Menta, I should quote from the good book. I could have quoted from Kurzweil's writings and others. This is one example of brilliant thinkers. I agree with everything in intelligence, except when I got to this, I really was thrown for a loop. I don't know if it's right or wrong, but it was very provocative. I think it was the most provocative statement in his book, page 219. I won't read it all. I'll just point a couple, like the bottom line. It's basically the cut and paste metaphor, that if you evolve this brain of the future, that you'll be able to do these instantaneous things, like download a new set of connections in your brain, instantly changing you from English speaker to a French speaker, or from political science professor to musicologist. So realize this isn't just at the periphery of I/O. This is deep into the cortex. Or that the business of building intelligent machines in the future won't look that different from installing new software. I would not have made that conclusion. I don't know how we can do that in the future, but I think it's a fascinating unresolved engineering challenge to say, if you do, in fact, evolve a system of that kind of complexity, can you do cut and paste of subsystems? Can you even partition subsystems or recognize them without going through a comparable level of reverse engineering as we're now doing with the human brain? And I would say you can't. At least, I don't see how you can. So what is it about involved systems that are interesting? First of all, they sort of create these emergent layers of abstraction. You saw the OSI stack that was presented by Mr. Schwartz just a moment ago. That occurs throughout evolutionary systems, as you know. And the great advances forward tend to pop to the top of the stack. So right now, most of evolution is taking place at the network level, at the topology of networks, not at the cellular level or the organelle level, right? We've long since sort of baked that in with a subsystem architecture as we go up. So the advance of humans over their predecessors wasn't so much reinventing organelles or the basics of DNA. It was at the expansion of the neocortex and maybe mirror neurons, but not much farther down the stack. So that creates some interesting partitions, right? We have organs, organelles, systems. We have a natural partitioning of biological systems. But when you get up to the network layer, within any one of those network layers, it becomes less obvious how you can partition, obviously, between and figure out where the speech or vision system of the brain is. It doesn't just fall out as obviously as where the heart is in your body, for example. So the second point is the main point of my whole talk. I think the subsystems are inherently inscrutable. And you see this time and time again in evolved or iterative algorithms. The example that I first came across was when I was working on neural networks. I actually tried to sell a company at Technosis a long time ago, but never got a call back because it was pretty crap code. But in any case, when you build neural networks, if they're any size or scope, you have no idea how they work. You have to spend quite a bit of time after it's done to figure out, well, what is the mapping, especially for the inner nodes with backpropagation networks and some of the early work there. Similarly, when bubble sort algorithms were involved as a genetic algorithm, and Danny Hillis did this work, he created a sorting algorithm that was better than anything he was able to write. It didn't beat the best human code, but it was better than anything he could write. He had no idea how it worked. He spent quite a bit of time looking at the algorithm that was evolved, couldn't make sense, heads or tails out of it. It worked pretty darn well. Same is true in a sociological sense in the wisdom of crowds phenomenon. And this may be different for some of the folks in the audience, but there is a lot of evidence that indicates in certain contexts a group of diverse thinkers can produce decisions that are better than any one member, even if some of the members are experts And none of the individual members can say how the decisions are being made. They just know the process of giving everyone an equal vote, not having groupthink, et cetera. The process works better, even though members aren't learning about how the decision was made. They're learning about the process of making decisions. And that's a metaphor we'll see time and time again. Oh, that's the next point. Then when you, in all these examples, neural networks, et cetera, we can learn a lot as we actually train these systems on how one builds neural networks. But the artifacts one creates, the system, the vision recognition system, doesn't necessarily just lend its secrets to us without quite a bit of reverse analysis. One might say reverse engineering is a term we're all familiar with, but not reverse evolution. And what you get, effectively, is a black box defined by its interfaces. And it takes quite a bit of work in engineering to look to the inside. At least that's my proposition that I put out there. I'm curious for counterexamples, maybe in the Q&A. Why would this be? Well, I think one of the reasons is it relates loosely to Wolfram's notion of computational equivalence and all the other people who said similar things before him, and David Deutsch and his idea also of quantum computational equivalence. And that is that you're going through a series of iterative mathematical operations in all natural processes. That any process in nature can be thought of as a computation. And if it's an iterative computation, there's no shortcut. There's no mathematical way, for example, in cellular automata, to jump to the answer, except for the trivial cases. If true complexity is going to emerge, if you're on the edge, if you will, between chaos and indeterminacy, chaos and determinacy, then you're inherently at a complex, interesting domain, and you inherently can't predict the future with a computational shortcut. So you have to run the algorithm. You have to do the iteration. You have to train the young, computer, if you will. And there's no shortcut. And therefore, there's no easy way to, sort of formulaically say, oh, here's how it works. Here's where the vision system's going to pop out in any way that's predictive before you actually do it. So I won't go through these points in detail, but if one were to think about a dichotomy, what are the differences between these two domains? You have a perception of control, you have predictability, you have efficiency in the sort of Germanic design tradition, if you will. You have things that are out of control, literally the name of a great book on this subject from Kevin Kelly. It's like raising a kid, perhaps. Systems over here are brittle. Just look at Microsoft's code. Things over there tend to be robust, resilient, adaptive, and can be transcended in their accustomed environment, right? So there will be a caveat there that says only in the domain in which you evolve a complex system is this true. If they're outside their accustomed domain, all these things may fall out the window. Generally, I'd say design applies to what we would now call simple problems, things that once you've done them, it's kind of obvious, and the big unsolved problems tend to be over here. And, oh, by the way, some of the solutions are very parsimonious and elegant. The analogy I love in thinking about these two domains is that the entire human genome, your genome, when burned to a disk in digital form, is smaller than Microsoft Office. Right? It's just an astounding difference in code compactness and processes.
And less buggy.
And less buggy, exactly. Here you have subsystem clarity, though. I mean, the key advantage here for the object-oriented programmers and such is code portability, cut and paste. The whole cut and paste metaphor, this is what the engineers love. Why do they go through some of these, if you will, problems? It's because at the end of the day, if you write a really good spell checker, you can use it more than once. And over here, you have to do quite a bit of effort to understand what's going on. Here you have modular reuse. Here you have this hierarchical subsumption architecture. I'll talk a little bit more about some of this other stuff, but there's some inherent issues with the way evolutionary algorithms work. One might say the selection pressures present some interesting embedded survival techniques, perhaps. And you might lead to what are called co-evolutionary islands. If you evolve one complex system over here in a custom environment with other artifacts, it may only work in that environment, and something else that's evolved over here without any connection between them may not interface very well, right? And it's an interface problem. And it's the same thing's true in the biological world. This is what we call sort of this false dichotomy between artificial and natural systems. If the natural world co-evolves with its external world, and the extent which something that comes in from the outside, it can ruin that. And differential immunity with viruses is one, across continents in the world is one area where in biological evolution you see that problem as well. So some implications. Last, I think, 2 slides. Basically, this cut and paste portability I don't think exists for the dominant paradigm that I see most people pursuing for artificial intelligence and cognitive computing in the future. I think it inherently won't be portable. The ultimate example of this, where Ray Kurzweil describes uploading your human consciousness to a silicon substrate, while I love the concept, there's still some issues to be worked out, for example, around phantom limb pain in V.S. Ramachandran's work on a simple thing with amputees, where you have this cortical remapping that takes place and causes intense pain and debilitating problems for some people. It wasn't fully understood. It wasn't obvious how that would fall out of the system. Similarly, this co-evolutionary islands point would lead to the conclusion that Honda's got it, spot on. You've got to be doing and so would Rodney Brooks and others would argue, you have to be looking at the sensory I/O, and your intelligence will be defined by that sensory I/O. And if you don't develop these systems with a view of what that sensory I/O is, the brain in the box would go stark raving mad. Of course, as I mentioned, the custom environment and the differential immunity point I think has already been made. This path dependence, you might argue that any evolutionary or selective algorithm that breeds for propagation of oneself might have a self-survival instinct. Will these AIs be friendly? Will they, is that something you program in? Is that something you can control? Is it inherent to the algorithm? Is an interesting question, and it will be defined by its senses. In fact, if you developed one of these in a computer, it would be like an alien intelligence, right? It's as if an intelligence appeared on Earth. With very little connection to us, unless it was a robotic intelligence much like us or uploaded from us. And an interesting thing is, would we ever bother to reverse engineer it? If you're on a silicon substrate, the pace of evolutionary advances will be so much greater than biological evolution that you could iterate a couple more times and get so much better, so much quicker that why would you ever spend the time to actually dive into a deeper research project to reverse engineer anything? If you upload an intelligence, right, the FDA rules will probably make you upload a primate before a human. Make sure it's a bonobo, not a chimpanzee. Right? Very important difference in terms of social structure. The bonobos are, hedonistic. Well, we'll just not get into their sexual habits. That's the model you want. Believe me, you don't want the chimpanzee. And the point is that this intelligence augmentation versus artificial intelligence is a bit of a horse race. You might say, hey, augment early and often if you want to be part of the future. I think it's more likely that something that bubbles up from the bottom up will outpace any attempt to bootstrap or bring humans along for the ride. But that's just a personal opinion. So I think the big unanswered engineering challenge of the future is, will these techniques bifurcate and diverge? The farther you go down one path, is it less and less the case that you can apply engineering discipline to what you're evolving? Or will they blend in ways that sort of, oh, yes, we know how to do this at the multi-level evolutionary. We can guide evolution better. There's a lot of research going on how to interweave these two, but it's not obvious that they're diverging or converging. I won't go through any of this, other than the last point maybe, that now we are purposely inserting ourselves into our own evolution. Right? The history of evolution has been, as it moves up the hierarchy of abstractions from sort of cellular levels to organelles to organisms to ecosystems and mimetic evolution itself, that we as humans are now inserting ourselves and will probably create the next phase of the evolution of evolvability itself. And in so doing, create organisms that are greater than ourselves. Right? There's no question looking back a million years from the future that humans will not be the end point of evolution. We seem to assume that many times. At least some people do when they have discussions about machine intelligence or the dangers of some of this. And that fear usually occurs when you think about some of these systems in the context of our current lifetime. But if you shift the framework and think about some of these artificial systems in the future, the question might be, would you want your grandchildren to be smarter and healthier than you? And in some sense, the sentiment can shift from this selfish desire for human supremacy to a universal human desire for symbolic immortality. And so I think there is a different framework in which you could look at this as a bold and good future that we're heading into. In the near term, I'll just end with a quote that's a bit more pragmatic. It comes from Danny Hillis in a wonderful little computer science primer called The Pattern of the Stone. He concludes, and I'll just let you read this, that we will not engineer an artificial intelligence. Rather, we will set up the right conditions under which it can emerge, and it will be the greatest achievement of our technology will be the creation of tools that allow us to go beyond engineering, to allow us to create more than we can understand. And that, I think, is the grand engineering challenge ahead of us. Thanks.